talk about ice charts. We use an ice chart when we're given initial concentrations and set up equilibrium concentrations. In the previous video, you learned how to set up equilibrium expression and how to solve for K or for an unknown concentration using the equilibrium expression. But in all those problems, you were given equilibrium concentrations. So in these problems, we'll be given initial concentrations, and we're going to find the equilibrium concentration. And so ICE is an acronym which stands for initial concentration, which has to be in molarity. C is the change, which is a stoichiometric change based on the balanced equation. And then E stands for equilibrium, which also has to be in molarity. And so if we look at the practice problem, we have 2 HI going to 1 hydrogen and 1 iodine. And we're told that we have 4 moles in a 5-liter flask of HI. So first thing we need to know is what the initial concentration is in molarity, and that's moles per liter. So we take our 4 moles and divide by our 5 liters, and we get 0.8 molar. Now I keep 3 significant figures because each of those 2 numbers have 3 significant figures. And initially we had no hydrogen and no iodine. Next we have to figure out what our change is going to be, and I said it's a stoichiometric change. And so for our stoichiometric change, we have to look at our coefficients. And so what we know is that since we have reactant and no product, our equilibrium, in order to get to equilibrium, we have to shift towards the products. So when we shift towards the products, we're going to lose HI, we're going to gain H and I. And so we call X our change. Okay, so since there's a 2 for every 2 HIs for every hydrogen and iodine, the change here is going to be a minus 2X. And then we're going to add X and X here because both those have coefficients of 1. And then to determine our equilibrium concentrations, we'll just add down. So we have 0.8 minus 2X and X and X. So then we want to plug that into our equilibrium expression. So our equilibrium expression is going to be our products raised to their coefficients divided by our reactants raised to their coefficients. And so that would be squared. And then we'll plug in our values. We're told that K is 0.016. That's equal to the value of equilibrium for H, which is X. For I is also X. And then for HI would be 0.8 minus 2X squared, because that was squared. Now, we know that X times X can also be written as X squared. And so since both of these are squares, we can take the square root to solve for X and make it easier. So we'll take the square root of 0.016, and we get 0.126. And that's equal to X over 0.8 minus 2X. And then we want to cross multiply. And we'll get 0.126 times 0.8 is 0.101. And then we multiply 0.126 times 2, and we get 0.252x, and that is equal to x. And then we'll combine like terms, so we'll add 0.252x to both sides. And we'll get 0.101 equals 1.252x, and we'll divide to solve for x. And then we'll find that x is 0.0807. And so that will be the value of x, which when we come back over here, will be the equilibrium concentrations for H and I. So 0.0807 molar and 0.0807 molar. And then we have to determine what the equilibrium concentration is for HI. So it's going to be 0.8 minus 2 times x. So 0.8 minus 2 times 0.0807. And I got that to equal 0.639 molar. So the equilibrium concentration for HI is 0.639 molar, and the equilibrium concentration for hydrogen and iodine are both 0.0807. So that's how we set up ice charts. What I'd like for you to do is to set up the practice problem. I don't want you to solve it. We'll talk about how to solve it in class tomorrow, because you'll have to use your problem solver on your calculator to do that. But I want you to go ahead and set it up and get as far as plugging everything into the equilibrium expression.